In recent years, the contamination of water resources continuously exists due to the release of organic pollutants from industrial discharges. Organic pollutants
are toxic molecular compounds
that could affect the fresh water quality, as well as cause various diseases in humans when exceeding the permissible limits. Industrial products such as detergents, petroleum hydrocarbons, plastics, organic solvents, pesticides, and dyes are vital sources of these organic compounds. There is a strong need to treat the toxic pollutants with a proper treatment option. Both biological and chemical methods have been applied to remove organic pollutants from water and wastewater.
Biodegradation is a process using microorganisms, fungi, green plants, and their enzymes to break down organic molecules into carbon dioxide and are mostly widely used due to its low cost and small impact on the environment.
However, some organic pollutants have the characteristics of lower water and higher fat solubility and are stable to all degradation processes. So, the conventional biological methods cannot be used for complete treatment of the effluents, and hence the introduction of newer technologies to convert it into less harmful or lower chain compounds, which can be treated biologically, has become imperative. Chemical oxidation technology is one of the newer technologies which change chemical pollutant to slightly toxic, harmless substances or transform it into manageable form. However, chemical oxidation technologies constitute the use of oxidizing agents such as ozone and hydrogen peroxide exhibit lower rate of degradation. Therefore, advanced oxidation processes, AOPs, with the capability of exploiting the higher reactivity of radicals in driven oxidation, have emerged a promising technology for treatment of wastewaters containing refractory organic compounds. Radical, also called free radical, in chemistry is a molecule that contains at least one unpaired electron. Most molecules contain even numbers of electrons, and the covalent chemical bonds holding the atoms together within a molecule normally consist of pairs of electrons, jointly shared by the atoms linked by the bond.
Most radicals may be considered to have arisen by cleavage of normal electron pair bonds, every cleavage having produced two separate entities. Each of them contains a single unpaired electron from the broken bond. Based on the sources for the production of radicals, AOPs can be classified into UV hydrogen peroxide processes, Fenton and photofenton, ozone-based processes, photocatalysis, sonolysis. We will choose photocatalysis, AOPs, as the example to discuss in more details. First, let's explain some of the terminologies. Catalysis is the process of increasing the rate of a chemical reaction by adding a substance known as a catalyst.
Catalysts remain unchanged after the reaction instead of being consumed. Photocatalysis is a type of catalysis that results in modification of the rate of a photoreaction, a chemical reaction that involves the absorption of light by one or more reacting species. By adding catalysts that participate in the chemical reaction without being consumed. TiO2 has so far shown to be the most promising catalyst for application in AOPS. TiO2 is highly photoreactive, cheap, chemically inert, and stable and non-toxic. Let's look at how photocatalysis works. When light energy is irradiated onto the surface of titanium dioxide, electrons are released, which bond with oxygen to become superoxide radical. The surface of the titanium dioxide becomes positively charged and take electrons from adsorbed water. The adsorbed water that has lost electrons become hydroxy radical, OH radical, which reacts with many pollutants, decomposing them through cracking. Then, the superoxide radical and hydroxy radicals are powerful enough to decompose organic compounds and turn them into water or other harmless substances. AOPS holds several advantages in the fields of water treatment. They can effectively eliminate organic compounds in aqueous phase without pollutant being collected or transferred into another phase. Due to the higher reactivity of hydroxy radical, it reacts with many aqueous pollutants without discrimination. AOPS are not therefore applicable in many, if not all, scenarios where many organic contaminants must be removed at the same time. Some heavier metals can also be removed in forms of precipitated metal hydroxide. In some AOPS designs, de-infection can also be achieved, which makes the AOPS an integrated solution to some water quality problems. Since the complete reduction product of hydroxy radical is water, AOPS theoretically do not introduce any new hazardous substances into the water. Let's look at some examples of application of AOPS.
Since bacteria and pathogens can be considered as organics in AOPS, highly reactive oxygen species ROS, such as hydroxy radicals, hydrogen peroxide, ozone, singlet oxygen, sulfate radical, and sulfur oxide radicals are formed in situ, which can initiate oxidation reactions in water to damage membrane, proteins, lipids, enzymes, DNA, and RNA of pathogenic microorganisms. Parabens are esters derived from p-hydroxybenzoic acid and many used as preservatives in cosmetic, pharmaceutical, food, and industrial products.
Parabens have been detected in the effluents of wastewater treatment plants and in drinking waters. The advanced oxidation process is recommended for the treatment of water polluted with parabens because it is the most effective process from an economic and environmental point of view